Welcome to the second video for Chapter 2, Section 4. We just went through a very complicated process of long division. Now we're going to start simplifying it and talking about special cases and how this can be a little bit more useful for us. So the first thing we're going to talk about is something we call the remainder theorem, and then after this, the factor theorem. The remainder theorem, we have to be kind of careful with this. We can only use it when we're dividing by what we call a linear idea. So x minus a number or x plus a number. And it's just going to help us figure out that overall remainder that we found at the end of long division. So instead of going through that entire process, we can follow this rule. So basically it says if we are going to divide by this linear idea, and they just make the rule as x minus k, to find the remainder, all we need to do is take the number part and plug it right into the function. Now you need to be careful with this because they write it as x minus k, and then they say plug in k into the function to find the remainder. So an easy way to remember that is to, whatever sign is in front of that number, you want to take the opposite of that and plug it in. So in our example, when we're looking at this function and saying what's the remainder when I divide it by x plus 3, I see a plus 3, I'm going to plug in a negative 3. So for this question, if all they ask us to do is find the remainder, we're just going to plug in negative 3 into the function. So we'd have 2 times a negative 3 squared minus a negative 3 plus 12. Okay, and try to do this through mental math if you can. Negative 3 squared is 9, positive 9. Multiply by 2, we'd get 18. We're going to have plus a 3 and then plus 12. So you put all those pieces together, we get 33. Okay, so the remainder, if we were to actually do that division, is 33. That just kind of seems like magic. I'm going to show you later on that is actually the remainder. But there's a proof for this. We aren't necessarily going to get into the proof in class. This is one of those things where if you take more upper level classes at some point, you're probably going to prove it. But for us right now, we can just kind of accept it. But what I want you to take away from this is that if we got a remainder of 0, that would be a good thing. And it may not be crystal clear right now why that's a good thing, but it is going to be something that we want to remember. And that's actually our next theorem. The next theorem is the same thing as, except we're going to call it a factor when our remainder is 0. So basically, you are doing the same thing. If we are dividing by x minus k and we get a remainder of 0, so this is the same sort of rule we had before, then we just call it a factor of that function. So we want to confirm that x minus 3 is a factor of this this cubic function. So to do that, we'd be looking for the remainder, and because we're now dividing by x minus 3, I'm going to plug in a positive 3. Again, take the opposite of that sign. So I want to look at f of positive 3, which would be 2 times 3 cubed minus 3 times 3 squared minus 5 times 3 minus 12. So I go through again, try to do this with some mental math here. 3 cubed, 3 times 3 times 3 is 27, times a 2 is 54. 3 squared is 9, times another 3 is 27, so we have a minus 27, then a minus 15, and a minus 12. So see if you can do this on your own. 15 and 12, right at the end here, that gets us minus 27. Minus another 27 gets us negative 54. Plus a 54 gets us 0. So they're saying our remainder is 0, therefore by this theorem, x minus 3 must be a factor. What does that all mean? Well, if something is a factor, that's a really good thing because all 4 of these are equivalent. So if I can prove that x minus k is a factor of the function, that means that I found that that k number is an x-intercept, or a 0, or we could also say it's a solution. So when we are actually able to say it's a factor, really that just means we found an x-intercept of this function. That's going to be very helpful later on when we try to graph these things. Then our last idea, I'm going to jump all the way down to the bottom of our notes here. It just seems to fit better with what we're talking about. This fundamental theorem of algebra. If we know that we have a polynomial that has a certain degree, we can have at most n, if it has degree n, we can have at most n zeros. Now, we can kind of split that between real and non-real zeros. So if we were to get into complex numbers, we could guarantee that if we're looking at something that has a fourth degree, there are going to be 4 zeros. But there are going to be 4 x-intercepts. I could also call zeros x-intercepts. But there could be something to the 4th power. It only has 1 or 2 or 3 x-intercepts that we would normally think of. And that's really all we're going to cover this year. We're not going to get into the complex numbers. But that is something good to know, that if you were dealing with something to the 4th degree and you thought you had 6 x-intercepts, you're probably doing something wrong. So beyond that, we're not going to do much with this theorem, fundamental theorem of algebra. So that's enough for me for this video. Jot down any questions, and we'll see you in class.